we're going to create what's called a reduction, sometimes called a recurrence formula. Now, what this is good for is those questions where you have to continually do the same process several times. And so you probably got to the power of something or something like that. And so you want to reduce that power down and get it to something more manageable. Integration by parts is by far the most common way of solving these problems. So let's just look at some. They want us to find x log x to the power of 3 dx. Now, okay, power of 3 I suppose is not too high, but it is going to involve doing integration by parts a few times. So let's create a formula. So in is going to represent x times log x to the power of n. And we'll do it by parts, so u will be log x to the power of n. Now in something like this, that is always going to be the smart thing to make u, because you're trying to reduce the power. So when you differentiate, you reduce the power. So du becomes n log x to the n minus 1 over x dx. So dv is x dx, which means v is a half x squared. So we get uv minus v du. But look what happens to our integral there. It's now in the same format, but the power is 1 less. It's still the integral of x log x to the power of something. So let's tidy this up. We'll work out the brackets over there. That turns out to be e squared on 2. And as I say, that second one I could rewrite as n on 2 times I n minus 1. And there's my formula that allows me to reduce it down without having to continually integrate and integrate and integrate. So the one that they've asked for is I3. So using my formula, I know I3 will be e squared on 2 minus 3 on 2 times I2. But now I can use the formula to work out I2. I2 would be e squared on 2 minus I1. And tidying that up, I get plus 3 on 2 I1. Now I1, and so I've now got e squared on 2 minus 3/4 I0, and in fact our integral now doesn't even have log in it, because we've got log x to the power of 0, which is 1. And all I've got to integrate is x, which is of course a half x squared. I can now sub in, let's tidy that up, and we get a final answer. So we reduce it down. Now there is another way of approaching this. Instead of reducing it down, some people like to build it up and actually start with the I0. So they'll go, oh, well, I0 is, and they work it out, it's a half e squared minus 1. And then say, well, I1 would be e squared on 2 minus a half times that answer I just got. And then they'll work that one out. So they now know what I1 is. But I2 is e squared on 2 minus I1. Substitute in what they found out for I1. Okay, we now know what I2 is, which then allows us to work out I3. So say you can reduce down or build it back up. The choice is, of course, yours. Personally, I go with the reduce down, but it's not wrong to do it the other way. I mean, if that's what you prefer. I say integration by parts is going to be used a lot of times, but don't get fooled to thinking you have to use it every single time. Here's one where we're not going to use integration by parts. We're just going to use our trig identity. We do an integral of cot. Now, if you call our technique for cot, it didn't matter what the power was, we used the same technique every time. So it makes sense to use that technique on cot to the power of n. So cot, I pull out the cot squared. The cot squared, I can make cosec squared minus 1, which I can now split into 2 integrals. The first one I can work out via a substitution. The second one, you'll notice, is the same as my original integral, but the power has been reduced by 2 in this case. So our substitution would be u equals cot x. Du would be minus cosec squared x. And so I have minus the integral of u to the power of n minus 2 minus I n minus 2. Subbing back in, we've got our formula. So this one will reduce by 2 every single time. Now, there's another way of approaching it. If with trig, because of trig identities, you very often end up reducing by 2 each time. If you don't have to use parts, and we didn't have to use parts in this one, another idea is to actually go, well, what is in plus or minus in plus 2? Because I know my formula is probably going to involve in and in plus or minus 2. Doesn't work 100% of the time because sometimes there might be a multiple of them. But anyway, let's see what happens. I'm going to see what happens when we add these two things together. In plus 2. I would get cot to the power of n plus cot to the power of n plus 2. Now there, I can factorise the cot to the power of n, and I get 1 plus cot squared. And so I have cot to the power of nx cosec squared. That I can do because I've got derivative times function to the power of n there. So add 1 to the power over the power. Now all I've got to do is rearrange it, and I've got a formula. In plus 2 is equal to this expression. Because I'm looking for a formula not for in plus 2, but in. I don't make in the subject here, otherwise my formula is not going to reduce my power, it's going to increase it. So all I do here is substitute in for n. And what I substitute in is n minus 2. So everywhere I see n, I replace it with n minus 2, and I get my formula. So n plus 2 becomes n becomes n minus 2, the n plus 1. If I substitute in n minus 2 into n plus 1, we get n minus 1, and so on. So there's my formula. Now, I'm not saying that's the best way of doing it, but it is an approach you could try. Let's now work out what cot to the power of 6 is, and we can see now the advantage of a reduction formula, rather than having to continually integrate and integrate again and so on. I can say, well, I6 is minus 1/5 cot 5 minus I4, and I4 is minus 1/3 cot cubed minus I2, but negative of all that changes into positive, and I2 will become minus cot x minus I0, and I0, well, that's just the integral of dx. Integrate dx, we get x, and there's our answer for cot to the power of 6. All right, again, integration by its parts might not be the only technique you use in it. So algebraic manipulation can come in handy, or maybe again we might use a trig identity. So this one here, 1 plus x squared to the power of n, they've given us a bit of a hint. It's going to connect in with n minus 1. So my u will be 1 plus x squared to the power of n, because my du now will reduce that power by 1. dv is dx, v is x. So uv minus the integral of v du. Now have a look at my integral. It's not quite in, because it's got x squared at the front. So this is where I do an algebraic manipulation. That x squared I'm going to rewrite as 1 plus x squared minus 1, because then I can split that into two integrals. 1 plus x squared times 1 plus x squared to the power of n minus 1, and minus 1 times 1 plus x squared to the n minus 1. But what that now does, in the middle, that becomes 1 plus x squared to the power of n. And so these two integrals can now be rewritten. The middle one is in, and the end one is in minus 1. I'm trying to create a formula for in, so I'll move the 2n in to the left-hand side, and now divide by 2n plus 1, and I come up with a formula. In the HFC, what normally happens, when you get a complicated one like this, they'll normally say, show it's this, so then if they do want you to use it, then you've got the formula you can use for the next parts. So something like that. Here's 1987, so something like this. We want to find the integral of cos to the power of n. They're telling us what the formula is. It's going to be that. And then we'll go and use it to find cos to the power of 5. All right, problem with cos. We had a different technique depending on whether n was even or odd. I don't know whether n is even or odd. They haven't told me. So I can't use one of those techniques. So I'm going to use parts. Now, I'm going to split it up into cos n minus 1 times cos. Why that? Because I look at the formula that they're asking me to prove, and I'm going to end up with in minus 2. So when I reduce that power by differentiating, I'm probably going to want to end up with n minus 2. So it makes sense that we make u to the power of n minus 1. Differentiate that, there's my n minus 2 in the power. That means dv is cos x, and we integrate that, we get sin x for the v. So uv minus v du. Okay, well, we can work out the brackets there. That's just going to be 0 when we look at it, because cos of pi on 2 is 0, and then sine of 0 is 0. So we can have 0 minus 0. That's just going to go away. Let's look at the integral. That's more interesting. We'll change that sine squared Let's change the sine squared into 1 minus cos squared, then split that into two integrals. And we now have cos to the n minus 2 and cos n, which is in the form of our question. So they're actually in minus 2 and in. Again, I can now move the in to the left-hand side. I end up with n lots of in, divide through, and I've got n. Okay, so we've got our formula. Of course, because they told me the answer, I knew there was a connection between in minus 2 and in. So I could try that way, and in this case, it comes out quite nicely. So in minus 2 minus in, subbing in, trig identity becomes sine squared. I still got to use parts though, so have I really saved myself any time? Possibly not. But there we go, uv minus v to u. We have our answer. Voila. As I say, did it really save me any time? Yeah, probably not. But it's another technique. Let's go find our I5 that they want us to find. So I5 will be 4/5 I3. I3 is 2/3 I1. I1's as far as I can go. Because remember, we're reducing by 2. I can't go I negative 1. So I have to stop at I1. Integral of cos x. Anyway, cos, we get sine. Sine of pi on 2 is 1. And so we have 8/15 as our answer. 2004, I put it in because it's such a nice question. It's in fact got two formulas to play with here. In is the integral of tan to the power of n, but then they've also given us this other one, jn, which is going to be minus 1 to the power of n, I2n. They're actually getting us to use the adding technique this time. So they're saying, hey, show that in plus 2 is this expression. Well, sub in, join them together, and look at what we got, 1 plus tan squared. They had a common factor of tan to the power of n, but 1 plus tan squared is sec squared. And I now have derivative times function to the power of n. Add 1 to the power over the power, and there we have it. Now I've done it via an actual substitution, but if you did notice it straight away, of course, then you don't have to worry about changing the limits and things like that. You could just go add 1 to the power over the power. But we get it. There it is, 1 on n plus 1. Deduce then that jn minus 1 will be this expression. Okay, jn minus 1. I sub into the formula they gave me. Minus 1 to the power of n, but that will be I2n, and then minus, and that will be I2n minus 2, because it's twice that value. But look what I've done there. So I can take out a common factor of minus 1. I've changed my minus times minus 1 to the power of n minus 1 to be plus minus 1 to the power of n. So basically I've just used my index laws. Minus 1 to the power of 1 times minus 1 to the power of n minus 1. But that allows me to factorise the minus 1 to the power of n, which I notice is in the answer I'm looking for. So I can do that. I'm left with I2n plus I2n minus 2. Okay, well we've got a formula. Now our formula was in plus, hang on, let's go back to it. What was it? in plus 2. So if I use that formula, but I let n be 2n minus 2, it's just minus 1 to the power of n times all that. So minus 1 to the power of n wasn't in the formula. Jm, we've got to show it's this. Jm will be minus 1 to the power of m on 2m minus 1 plus jm minus 1. Okay, because we've just proved that jn minus jn. So all I've done is I've moved the jn minus 1, if you like, to the right-hand side and created a formula. Now I use the formula again, because jm minus 1 will be this expression. But jm minus 2, I can use the formula again, and so on and so on and so on, and it will reduce down to j0. So eventually I'll get j0. The trick, of course, is working out what the term before j0 was. And it'll be minus 1 to the power of 1, because that will be when n is equal to 1. And then on the bottom then, we'd get 2 times 1 minus 1, which is 1. That is the sum that they want if you look at it. They're saying the general term is minus 1 on n to the power of 2n minus 1, going from 1 to m. Well, that's exactly what that sum is saying. Now all we've got to do is work out j0, and hopefully the answer will be pi on 4. So integral of dx going from 0 to pi on 4, yes indeed, that's pi on 4. Use the substitution u equals tan x to show that in is this expression here. Remember, in was the integral from 0 to pi on 4 tan to the power of n. So u equals tan x is the same as saying x equals the inverse tan of u, and that's going to be a heck of a lot quicker. If I make it x equals the inverse tan of u, have a look what happens to dx. dx is du on 1 plus u squared. Work out the limits. But that now means tan to the power of n is u to the power of n. dx is du on 1 plus u squared, and it just drops out nicely. We've got what they want, u to the power of n on 1 plus u squared. So that wasn't part of the last one, that was just an additional question there, or was it? So there's another way of writing in. Okay, here comes the last part of the last example. Deduce then that in is in between 0 and 1 on n plus 1, and conclude that jn approaches 0 as n approaches infinity. Well, I certainly know that that is always going to be positive. So that integral, therefore, is positive. Now, we know in plus 2 is 1 on n plus 1. If I rewrite that, I can say in is 1 on n plus 1 minus in plus 2. But hang on, we just said that in, or in plus 2, or anything, is always positive. So therefore, in must be smaller than 1 on n plus 1, because we're taking something away. So that gets one side of that inequality. But we also said that it's always positive. That gets the other side of the inequality. So 0 is less than or equal to in is less than or equal to in plus 1. But what happens as n approaches infinity? Well, as n approaches infinity, 1 on n plus 1 approaches 0. Therefore, we have actually trapped in between 0 and 0. So that limit must be 0. Okay, that wasn't the limit they asked us for though. They asked us for the limit of j. Well, jn then would be the limit as n approaches infinity of minus 1 to the power of n I to n. But we just said the limit of in, which could be anything, because we sub anything in for n, is 0. So therefore the limit of jn is also 0. 4h, we're going to play with reduction formulas.